Welcome to This Explainer. Before you even stepped out your front door this morning, you probably interacted with a dozen of these completely hidden computing heroes without even realizing it. Today, we're diving deep into the unsung technology that's literally powering our modern world, embedded systems engineering.
Let's start with a really relatable question. What actually makes a washing machine think? When you press start, how does it know exactly when to fill, spin, or drain? Now, you and I both know it's not running on some beefy Intel Core processor like your laptop. So what's really pulling the strings in the smart devices we use every single day?
Well, the answer is an embedded system. Look at it this way. Unlike your smartphone, which is a generalist, right? It's built to juggle Spotify, web browsers, heavy games. An embedded system is a pure specialist. It perfectly integrates hardware and software to do one specific job, and to do it flawlessly. Because they aren't bogged down by a bunch of background apps, they are incredibly efficient and highly dependable.
Okay, let's dive into this. Here's our roadmap for the explainer today. We'll start with the invisible brains, look at the anatomy of a system, explore where hardware meets software, open up the engineer's toolkit, and wrap up with why this is a future-proof career.
Section 1. The invisible brains, the hidden heroes of modern technology.
These systems are absolutely everywhere. In your living room, they are the brains inside your smart TV or your microwave. Out on the road, modern automotive engine control units and things like anti-lock brakes completely depend on them. They operate life-saving medical equipment, think heart monitors. And on a massive industrial scale, they are driving robotics and basically the entire Internet of Things. If a device requires any sort of intelligent control, you can bet an embedded system is quietly running the show behind the scenes.
And this brilliantly illustrates exactly where embedded systems divert from traditional software engineering. A traditional software developer usually focuses purely on code for general-purpose machines, mostly living up in the cloud or within a high-level operating system. But an embedded engineer, they literally have to marry their code directly to the physical metal. We're talking about building task-specific systems that require low-level programming to manipulate raw hardware. It's a totally different beast.
Moving on to Section 2, Anatomy of a System. Let's look at building the brain. So at the core of every embedded system, you essentially have this beautifully simple loop of data that relies on four main pillars. First, you have input sensors pulling in real-world data, like, say, a sudden drop in temperature. That data flows right into the processing unit and memory for logic execution. Finally, the system triggers an action, an output, like spinning up a motor. And the whole shebang is tied together seamlessly by communication interfaces.
Now, right inside that processing unit, engineers typically choose between two paths: microcontrollers, or MCUs, and microprocessors, MPUs. An MCU is basically the ultimate all-in-one package. You got your CPU, memory, and peripherals packed onto one cheap, compact chip. That's your washing machine brain. MPUs, on the other hand, are the muscle. They handle heavy, complex processing for things like advanced medical equipment or car infotainment systems. But they actually need external memory to function, kind of like needing an external hard drive for your own brain.
Section 3. Hardware meets software. High stakes and real-time responses. Think about this for a second. In general software, if a web app crashes or lags a bit, whatever, you just refresh the page. It's an annoyance. But you can't exactly Control-Alt-Delete a car crash. In embedded systems, missing a processing deadline causes catastrophic failure. An airbag must deploy in milliseconds, no exceptions. It is a strict, non-negotiable, real-time constraint where absolute reliability is, literally, a matter of life and death.
To guarantee that bulletproof reliability we just talked about, engineers use strict memory separation. The core instructions, the firmware, are locked safely away in flash memory, which survives even if the device loses power. RAM is kept exclusively for temporary runtime data. And if the system needs to remember crucial configuration settings after a power failure, it relies on EEPROM. This strict separation ensures the code absolutely cannot be accidentally overwritten, keeping the device totally 100% predictable.
All right, Section 4, the engineer's toolkit, the skills needed to build the invisible.
So the crucial point is, because these systems operate with razor-thin resources, sloppy code is just a total no-go. You do not have gigabytes of RAM to waste here. That's exactly why strong low-level C and C++ skills are absolute musts. Engineers also have to master RTOS, real-time operating systems, to strictly manage task scheduling, right alongside communication protocols like UART, SPI, I2C, and CAN, just so the physical components can actually talk to each other. And you'll find that an embedded workspace looks really different from a standard web developer's setup. While they use specialized IDEs and compilers to translate that high-level code, the real heavy lifting happens with debuggers, emulators, and simulators. Because you are bridging the digital and the physical worlds, you have to rigorously simulate those interactions, hunting down tiny bugs and timing errors long before your code ever actually touches a physical circuit board.
Which brings us to Section 5, a future-proof career, building tomorrow's brains. If you're looking to upskill, the path here is incredibly rewarding. You generally start out with a solid foundation in electronics or computer engineering, perhaps grabbing some specialized certifications in IoT. That foundation unlocks roles like an entry-level firmware developer, and as you master making that hardware and software sing together, you can rapidly advance to a senior embedded engineer or a system architect, where you are literally designing the technological frameworks of entirely new products.
And honestly, the field is only accelerating. We are rapidly moving away from relying purely on the cloud. Thanks to edge computing, the processing actually happens right there at the device level. We're now seeing AI integrated directly onto the metal, meaning tiny little microcontrollers can perform image and voice recognition instantly on the device itself. And naturally, locking down all these interconnected devices with advanced hardware-level security, like secure boot and encryption, is becoming a massive industry priority. Embedded systems engineering isn't just about making household appliances tick anymore. It is the absolute foundation of autonomous vehicles, smart cities, and edge AI. It's a discipline that firmly bridges physical reality and the digital frontier. So I'll leave you with this. As AI and the Internet of Things expand into literally every corner of our lives, are you ready to engineer the hidden brains of tomorrow? Thanks for joining me for this explainer.